All right, thanks. So yeah, I'm going to talk about image analysis with scikit-learn and PySpark working together, and how these form a use case for Anaconda cluster, which is a tool for deploying clusters on EC2 or DigitalOcean or other cloud providers. Whoa, sorry about that. So talking about PySpark and scikit-learn and scikit-image. So scikit-learn and scikit-image are applied to each image in this image search engine, and PySpark is used to do joins and clustering among all images together. So there's part of it that could be run and tested on the local machine, that's the scikit-learn and scikit-image, and then there's part of it that uses the cluster and PySpark. And so what the goal is of this image analysis project is to line up similar images. So if you had a historical image that looked like that, you should be able to line it up with a obfuscated version like that. And so I used a faces data set from that's used in face detection training, and did the code on the left to obfuscate the photos, and then see if I could find the fuzzified version in the original with the search engine. Oh. So here are some helpful links for this demonstration. There's the GitHub repository that's public, and I can walk over to that. That's right here at continuum.io/image analyzer, and that has the PySpark and scikit-learn Python files. It has a run helper file for submitting the codes to the cluster, and it has an iPython notebook and this presentation. And you can also view the iPython notebook on MB Viewer as a read-only version. So basically the steps of the image analysis example are to put a lot of images from the face training data set on HDFS, the Hadoop distributed file system, using commands like this, and then to run measurements on each image using PySpark to parallelize the embarrassingly parallel process of doing scikit-learn measurements on each image. And then there's the clustering among all images together that's done with PySpark. And then PySpark does joins and various similarity matching to line up similar images. So to go through some of the measurements that we're doing on each image, we're doing k-means, which is an unsupervised clustering algorithm. And there's a good documentation for the function we're using from scikit-learn right here on the color quantization example. So they are starting with an original image that has 96,000 unique colors, and using k-means to quantize the image into 64 representative colors that are more representative than 64 chosen at random. So that's kind of what we're doing on each image, is to do the k-means on each image with the fixed number of centroids for each image, and find out what are the most representative colors for those images, and then similar images can be joined on those. Another thing we're doing on each image with scikit-learn is word clustering. And there's a really good demo on this with the scikit-learn documentation. But basically, word clustering is an unsupervised classification that finds pixels that are similar in color, but also tends to prefer clusters that are contiguous in space. So that's why it's selecting out regions like the face that are a distinct color, and different regions of the hair that are different colors. And what we do with this in this image search engine is to take the geometries of those clusters and hash them in a scale-independent way so that we can find shapes that are similar between different images, even if maybe the grayscale changed or the lighting changed. And then another thing we're working on each image is perceptive hashes, which is basically to convert an image to grayscale and then encode it as 1 if the pixel's value is greater than the mean grayscale, or 0 if less than. And there's a good blog about that on Hacker Factor, walking through taking this original image, sampling it down to 64 pixels, and then calculating the average color, and then constructing a 1-0 bit array to indicate whether each pixel is greater than the mean, and then finally writing that out as a hash. So that's how we're using perceptive hash here, and there's different ways you can control its specificity by controlling how much you downsample right here and how much of the image you put into the hash, like if you do just partial images or the full thing. And we've experimented with doing the full image or doing it in chunks as well. And so what you get out of that function on each image is a dictionary that looks like this. So, well, a tuple, I should say. The first is the file name it came from, and then the dictionary of all the measurements on the image that are NumPy arrays, each one of them. So we can, by persisting these dictionaries in a Spark resilient distributed data set, we can subsequently map them and do whatever we want with them, check them, and use them for finding patterns among images together. And so that code that we've seen there to make those measurements on each image can also be run on your local machine just using the scikit-learn stuff. So you can run it on one image, and so this sort of sets up the configuration for those different clustering algorithms, and how many clusters to take, how much downsampling to do, and then you get out that same dictionary we just looked at. So that's pretty helpful when you're developing code with PySpark, is to develop it in a way that each function that you're going to map can be tested locally outside of all the setup of PySpark. So then after mapping through the images and calculating those image measurement dictionaries for all the images, we do a k-means on all the images together. And there's some code in here related to that. Basically, we have done our own k-means function right here using mapping the distance function and then reducing by the closest distance. And I did it myself here rather than using the MLlib k-means, because I also wanted to keep track of hashes within each k-means cluster to provide a sort of secondary classification. So to provide the ability to join based on cluster and a hash from a perceptive hash or a word cluster. And so this gives an example of some of what we can end up from after that is a lot of different lookups that look like this, like a hash from either a perceptive hash or a word cluster, or a file name, or this hash could be a cluster from the k-means of all images together. So that's what search.py does, is assembling all those flat lists. And then the main part of the searching is to take some new hashes, the candidate hashes, and the old hashes, and join them together. And so you might have this shows the old image, the original from one source, and the new image has the same hash in it. This is a hash of a partial image, and a different file name. So we end up with a lot of tuples that look like that and need to group by the hash and do a sort of vote count. So that's what it looks like after you've, if you've joined on a hash and you have 2 votes for that, two different file names that had that hash in it. And so this is an example of how you would do that kind of vote counting in PySpark. So we start with what we had before, the join that creates joining the old hashes to the new hashes on a key. And then we have the group by key, so that makes the key be the hash and then an iterable as the second item, x1. And we can iterate through those and find which file name had the most occurrence, which file name matched up with it the most, and reduce by that count keys function and end up with something like this. So this shows for a particular candidate image that it did find the original from the original folder, and it had these other matches that didn't match enough to be the top voted one. And I think a lot of those extraneous other matches are related to the background of these photos all being the same. So to go over the DevOps details, they're actually pretty easy. And that's the fun part of this talk, is how easy it is to build something like this with Anaconda cluster. This sort of gives you an overview to getting started with Anaconda cluster. And there are 3 basic steps for starting the cluster the first time after you've installed Anaconda cluster with Conda. The first step is to set up a provider's YAML file. So this is just a text file configuration that says, what is the cloud provider? Is that EC2 or DigitalOcean or another one? The secret ID and key for that cloud provider. A key name. So when you have a cloud provider, you have a remote key and you have to download that. And when you download it, you should have a path to where you have downloaded it. So those are all related to security of the cloud provider. So that's the first small configuration file you need. And then the second one you need is specific to your particular kind of cluster you want to start. So this one says, this is a profile for this for Spark clusters that I want to start. And it links back to the provider YAML file we just created, and it said we want to do AWS East. We want to have a 2-node cluster. We want to start with this machine image. We want to do a large instance type. The user by default is Ubuntu. And these plugins are different sort of managed plugins by Anaconda cluster that do a lot of DevOps details that will save you a lot of time. Particularly in this case, this plugin, Spark Yarn, that sets up Yarn and HDFS and Spark throughout the cluster. And all the configuration files for the cluster to talk to each other. And it also configures the iPython notebook, which is helpful for checking the results. And the overview on profile setup has a little bit more about some of the plugins and details you can put in there. So then the last step, now that we have our 2 config files and we have Anaconda cluster installed, is to create a cluster with any name, naming a profile we've already created. So that's a YAML file that we have in the Anaconda cluster directory. And then some more things you might want to do with Anaconda cluster are to put some files on the cloud. So this command at the top would put some file.py into the temp directory, and the target says do that for all the nodes on the cluster. This one is the same kind of idea, but it's pushing a whole directory of data. and it's only doing it to the head node. It starts a zero-based node numbers. So you can push to 0, 1, or put to 0, 1, or just 0 for the head. Another thing you can do with Anaconda cluster is get a file off the cloud after you've created it. So with the get, it's really important to use the target, because if you don't use the target, it defaults to getting it from all machines and naming it by the same file, which doesn't usually make sense. So what you would typically have is different things going on each node if you needed to do this. And on each node, they might be called the same thing, but then when you retrieve them, you want to have them named something else according to the node they came from. Anaconda cluster uses Conda remotely. So these, you just take a normal Conda install command, and you put a cluster in front of it, and then it does it on the cluster and installs all those dependencies, or can list what you have installed. And then this is the last thing we do when we're ready to run is to submit a Python file with the stream argument, and then it will stream the output as it's going. And we can also run any remote command on some or all of the nodes. So this is doing an ls on all of the nodes of that directory. You could also do something like git clone some repo and then cd into it and then install it. And you can get a list of all the clusters that are running. And that's helpful because it has the IP addresses, and you need to take this head IP address out, and that's where the iPython notebook is when you're looking for it. You can also look at the metadata for a specific cluster. So while my Spark cluster was running, it had this file right here, which is the actual cluster file. So we had the two configurations, the provider and the cluster profile, but those are both general because the cluster profile is for any Spark cluster that would be started under a profile like that. Whereas this cluster, actual cluster file that we're catting out in cluster.d is the actual cluster as it's created with IP addresses and other identifiers. So this is the file you would want to transfer to someone else if you wanted them to be able to also use that cluster. So you would transfer this file, and you would also have to transfer this key to them and have them put it at the same place or change this around to where they put it. And then it should work for them to do all the things on the cluster that you can do. And then finally, you destroy the cluster. So it takes care of all the instance creation and instance shutdown for you. And the nice thing about how it's done in Anaconda cluster is you say you want to destroy it, and it asks you for sure, and then it just shuts it down, and you don't have to wait for it to go through all the cycles of actually shutting it down. It gives you feedback right away, and you can close your laptop. And so far I've just talked about PySpark and the notebook, but there are a lot of other plugins that can be managed through the plugins in the cluster profiles. So that gives us an idea of the tools we're using for this image analyzer example. And we can look at the run helper to see how it uses a lot of those commands that we just looked at. So we start out by installing Python image library and NumPy. We have to get the unzip to help with the data files. We do these remote commands to run a bash script that does all the Hadoop file system put commands. And then We put on the cloud these the files from the repository that are important in Python and the configuration file. And then finally, we stream the mapper code that has the Spark context in it. And so, yeah, so that installs everything, downloads the images, runs through the measurements, and does the searches and everything. And while it's running, it's helpful to check its output. And the Anaconda cluster sets up these helpful URLs, the iPython notebook. You just have to replace this with your head node IP. Web HDFS is useful when you're doing Spark to check and see if files are appearing. The Web HDFS is just a web browser of the Hadoop distributed file system. And then the Yarn cluster monitor basically tells you about the busyness of the cluster, whether it's taking all the capacity or whether it's hung waiting for something. And those are all configured automatically with Anaconda cluster. And there's a full list of all the services like this in the documentation and which port to find them on. And then after the model run, I made this iPython notebook, which is in the it's in the repository and also on MB Viewer. But basically, this walks through looking at some of the results and working with PySpark. So this uses the configures PySpark right there with the Spark context, and then we can look at the pickle files of results. Like this is an example of measurements on an image. And then scrolling down, we can see there's a little bit of code around the vote counting and an example vote counts dictionary. And then finally in here we do where we are loading images with string IO from the Hadoop distributed file system and labeling them and seeing if we got the right match. And in this batch, I got all but one of them correct, except for that one. And then finally at the bottom, it shows the complete configuration that the model was run on to produce these results. And so that's what I've got. Any questions on PySpark or Anaconda cluster?
Yeah, Peter, I was just wondering, like, where for those methods that you mentioned about how you're doing the clustering of the images, you sort of came up with this method to mess with the images. Are there applications where you would find images in the wild that have been messed up in a certain kind of way where I don't know, like, are we talking about like security camera footage to match up with some picture of a person? Or?
I was thinking of just the same person in different photos that are not obfuscated on purpose, but just represent different positions or different photos. Okay. And I think that this method of lining them up could be pretty robust for finding the same person in different positions because it doesn't rely on sort of like wavelets like OpenCV where of identifying a face specifically. It's based on the colors of the image and not really finding faces specifically. So it could potentially line up some images on a similar background. So there's some positives and negatives to that.
What kind of run times for after you spun up the cluster, how long did it run?
On this group of like 50 images, it was taking a couple minutes. It highly depends on what you resize all the images to when you start. Okay. Yeah, that's the main. And also, how many perceptive hashes you create, because if you create one perceptive hash for each image, you can only match the full image, but you create a shorter list of things to join in the end. Whereas if you fragment it up and do a lot of perceptive hashes, then you end up with longer join operations. And I'd actually be curious to see how maybe some different, more Pythonic tool in place of PySpark works for this. Like, say, taking a lot of what's already been written and thinking about it a different way, maybe DAS distributed or something like that.
So it's a question specific on Anaconda clusters. Are you planning to support Azure for that?
For Anaconda cluster, I think Travis can answer that better than I can.
It's on the roadmap. Just a question of priorities. Right now, public clouds are definitely going to be supported. And in fact, spinning up Anaconda cluster on public cloud, you'll be able to do that basically free, pay for your resources. Right now we're primarily for helping people on their private cloud. That's what it's geared towards. But use cases in public cloud are definitely on the roadmap. And Amazon's the first one. But Azure is definitely we're talking to the folks. Make that easy.
Okay.
To that point, what kinds of clusters can you really spin up? Talk about Spark. Talk about Hadoop.
You could do.
The breadth of,
There's also iPython parallel, so that's another plugin that's managed.
Can I just talk to basic bare machines? Do I need to have some other cluster management software running already? Or?
I think you can do it on a bare metal machine, and the main thing you need is that cluster configuration file. This file. So by getting to this end cluster metadata file is how you could apply this to a bare metal cluster. It's been a while since I've been through the steps on that, but it can be done.
So in this case, just by creating Spark standalone cluster and
It creates a Spark cluster that has the Yarn client, and you can run it in local mode or with the Yarn client thereafter.
Okay, well, I think that's everything. So now I think we're just going to do lunch, but I don't know how long lunch is, but I think we're all dismissed to go get some, and hopefully there'll be enough this time around. Thanks, Peter.
Sure.